we are talking about electric potential and potential energy. You know what potential energy is, but what the heck is a potential, right? I will take an example with the gravity, because we are familiar with gravitational potential energy. But more importantly, what is a line integral? See, this work or potential energy is defined like this. Negative of F dot, this is a dot product, and ds, or dr, according to our multivariable calculus book, but whatever, it's a path. So it's called a path integral. It's a better name, but they call it line integral. Okay, so how do we evaluate such a thing? Let's take this example of gravitational potential energy. Then I will explain what potential means. Okay, suppose here's the x-axis, horizontal, and y-axis is the vertical, so we'll take a two-dimensional case. Okay, and then let's say this is point A, right here. Here's a point A, and here's a point B. And then we want to go there in this path, from here that way. Right, and then let's say this height right here is h, meaning this height is h. So we expect our answer to be mgh. Our potential energy, we want it to be mgh, right? Because that's what we learn in mechanics. But can we integrate and figure this thing out? And this, we'll get to the bottom of why there's a minus sign in potential energy here, okay? So first, we have to find the parametric equation of this path. I mean, there's a way to go this way and that way, but after this, it'll be pretty apparent on how to do that. So we'll call that the path C. So C describes this path. Okay? Now, the vector function R, for the people who have never seen vector function, parametric function x sub t, do you see it is, we can just write it like this. Oh, depend on what this angle is. Let's say this is h as well. So 45 degrees, eh? Just diagonal path. And then y is equal to t. If we do it like that, then h seconds later, will arrive at this point, h. So the coordinate here is h comma h. That makes sense to you? Okay, then let me introduce a vector function to those who have never seen it. Vector function R, it is just this parametric equation x, I vector, plus your parametric y, they are both function of t, j vector. Did I put equal sign there? J vector. Good. So in this case, it's just t I vector plus t j vector, right? Or you're more familiar with this component notation. You know what I'm saying? But it makes more sense to use unit vectors, so we'll just take that off. So far, so good. Okay. So that's our path. Then what is dr? You see here ds, dr, this is some kind of path integral. You know what I'm saying? So dr happens to be derivative of this, so just I vector plus just j vector times dt, isn't it? dt I vector plus dt j vector, if you will. Good? Okay, so what that represents is this tiny little infinitesimal movement. Okay, that's our dr, or in general ds vector. So far so good, and that's composed of this little movement, which is dx vector, and this little movement, dy vector. Okay, and we are just both calling it dt as much. Okay, then we have a vector field, and our vector field, of course, gravitational field is negative g, isn't it? Well, negative mg j vector. Good. It's just going down by magnitude of mg. Okay, then we'll evaluate this integral. Okay, so we'll evaluate this integral f dot ds or dr. Okay, so we have to take a dot product, and from t is equal to 0 to h. Actually, we'll just write it as curve C. This is general form. Or if your physics book uses ds here. Okay? Okay, now, then we have to take f dot product with this thingy. Okay, let's see what that does. So this thingy has no I vector, so that part is 0. I'm going to do it quickly here. F dot dr is, if component notation that you're more familiar with, 0, negative mg, and then dot that with 1 dt. You know what I'm saying? And then the first term is 0, and second term is negative mg. And then we have dt. That's all we get. You see how this line integral or path integral works? So we just take a dot product between your force, this is F, and your dr or ds, whatever you call it. And this ds comes from parametric equations. So we have to be intimately familiar with parametric equations. Good? So let's put in here. So this is negative mg and then dt. And from t is equal to 0 to h. So far, so good? Do you see this will give us a negative value? Right? This will give us an potential energy. We like this to be positive energy. Does it explain why we define potential energy this way now? Why that negative sign is there? Otherwise, we get negative energy. You get it? So when we say F dot ds or F dot dr, this is defined by work done by the field. So if you go down, if this is some kind of incline and your object slides down, then work done by the field is a positive quantity. But it's this idea. I'm going to put it right here. Here's a pool. Here's a potential energy pool. And this is a work, right? And then if initially it's like this, but, right, as one goes down, the other goes up. You know what I'm saying? They have to be opposites of each other. But change of delta U has to be opposite of delta W. You know what I'm saying? So that makes sense that we need this negative sign in front. Otherwise, we are looking at negative potential. Depends on definition, we can define it like that, but that's very inconvenient. We like the higher potential energy, higher elevation. That makes sense. So that's why we define this thing such a way, just to have this potential energy to be positive. Easier way I like to think is this F dot dr or F dot ds is work done by the field to the object. And this negative F dot dr is that amount that you have to do the work in order to store the potential energy in that position. How's that? So negative sign, it just depends on which you want a positive answer or negative answer at the end. Okay, now we'll continue. And this will be, so now we have negative sign there, remember, right? And they cancel each other. I like to change the color back. So this is positive mg t from 0 to h, correct? Okay, now, and then of course substitute, then we get our familiar mgh. Okay, so that's the potential energy calculation. Then what the hell is potential? Not potential energy, but potential. Okay, this is a huge concept because in E&M, this matters a lot more than potential energy. Then I will show you how to calculate one from the other. See, potential energy depends on the mass of your object. doesn't it? But if you are just purely thinking about the Earth from this point to that point, that's what's independent. In other words, potential energy difference between here and here due to a unit mass. Get it? 1 kilogram. How much is that? So it's just, that makes sense to you? Then from here, if you want to calculate potential energy, then you multiply m. So m times v. That makes sense to you? So far, so good? Okay, so let's define what potential is. Okay? Potential definition, let's put it here. Potential V is equal to, I'm going to put both of the definition. U is equal to integral curve C, parametric, and then F times ds, F dot ds, okay? In our case of electric field, and this is, I'll just write it as F. Do I want to do it? Yeah, electric field. Our F is Ke from last time, electric field, right? Time dot ds is potential energy in E and M, or where potential itself is, you divide this, I think I screwed up, KQ, we're missing Q, KQE. Good? Because you have to multiply it. Remember the force is Q1 times Q2, right? That test charge, Q naught, we'll call it. And then we, in this case, we divide this by M or charge Q. You get it? So potential, the definition is K E. You know what I'm saying? Ah, actually, oh, I really screwed up. K is built into the electric field, so it's just, let's try Q naught E dot ds, and this is just E dot ds. Your field dot product with the path, and then you integrate. Good? And then later, if we multiply this by Q, or in this case by M, then we get our potential energy back. Good? And then, of course, I forgot negative sign. How's that? Good, 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 good. Now, see, generally this works if it's a nice simple case, Cartesian coordinate, and then, right? And then we can make this thing even curvy, parabola, and it works out just fine. Our problem is our electric field goes out in radial direction. This is polar coordinate. And taking a dot product in polar coordinate is very, very complicated. And we really don't want to do it. We just want to find a nice system to get away from it so we can generalize it. So let me propose a different idea, okay? And different idea is this. I'm going to redraw this same diagram and do the same thing in a different way. So we have this axis right here, and our path was something like that. Let's say that's our path. Okay, and the field lines, remember field lines is downward, right? I'm gonna, this is G, downward, okay? Let's draw a tiny little ds right here. That is direction of ds. And then remember this, we split it up into I vector, J vector, and then took a dot product that only gave us the vertical component. But idea is this. So if we have F or F dot ds, could we just look at it? F is of course mg. Right? And then instead of taking a dot product, could we just put ds scalar and then cosine theta? Theta being this angle. That makes sense to you? Because remember, yeah.
Sorry, I think the sine theta, but yeah.
Angle in between, remember A dot B, yeah, theta is between the angle between two vectors. This is equal to A magnitude, B magnitude, and cosine theta, right? Actually, this is a very topic I'm going to be covering tomorrow. So we can do it this way. And our data, of course, happens to be 45 degrees, right? So, or 45 degrees, not that data, this data is 3 pi over 4. Okay? So what we have is, I'm going to go back to F here, and then write mg here. Mg ds. What is cosine of 3 pi over 4? Oh, come on. Fine. Negative root over 2, also known as this. Good. So this is what F dot ds is. Okay? Let's try calculating same potential energy. Remember, negative, right? F dot ds past C. But we know all of this. Good? So we have negative. With that negative sign, another negative here. Isn't that nice? So they cancel. They are designed to cancel. That's why that negative sign is there, right? The dot product. And then we have mg and then ds. Okay? S is this entire distance, isn't it? How long is it? Remember, this way was h, right? Do you see this is square root 2h? So 0 to square root 2h. Isn't this beautiful? So we have 1 over root 2 mg s now from 0 to root 2h. Substitute, root 2 cancels, so we get mgh back. Do you see these two are equivalent of what we just did? We can find the parametric equation and find the vector function, take a derivative, dot it with our field, and compute the integral that way, or we can just purely use the angle between the two and then use the term cosine. Good? Okay. Now we'll get to our situation. Because all of the charges for our purpose, electric field goes out in a radial direction. Radial meaning, this direction, right? This is the direction of the electric field going out, okay? So, and then we want to just take any arbitrary path, we call this thing C, from point A to point B. So it has got whatever the three-dimensional, really, coordinate, x1, x2, x3, x1, y1, z1, and then x2, y2, z2 is this thing. And then we want to calculate the potential, okay? So we'll calculate the potential of that thingy. Okay, potential here, space, is this path, and same as a negative sign here, and then E dot ds. So far so good? And then later when we multiply this by the charge that we are bringing in, then we get potential energy. Because the potential energy has to depend on the amount of charge that we want to move from here to here. Good? Okay. Well then, ds. ds is this little infinitesimal arrow that you see over there. Good? And theta is the angle between this and the electric field. And I'm going to just throw that electric field. Electric field goes out in that direction because it always goes out in a point charge like that. So far, so good. So let's calculate that part. So we need, let's call it dV. Not the volume, our potential is negative, negative later. Whatever. You want to put negative here or not? E dot ds. That's what we need. And like we did before, the magnitude E, whatever it is, and then we want to multiply this by ds and cosine theta. That makes sense to you? Okay, now let's zoom in and take a look at this triangle. We have a right triangle here, right? So ds times cosine theta is this side now, isn't it? Adjacent side. And that is what we call dr, the radial increase, right? Because if you think of this as a polar coordinate having some kind of, you know what I'm saying? That's dr. You get it? So it purely depends on our distance away from our charge, which makes sense, right? So we're going to write this as E. What is our electric field? Was it K, Q, this Q, the amount of charge, correct? Over R squared, R being this distance, R, and then cosine theta, which is ds cosine theta, which is dr. That makes sense to you? So far, so good. Let's substitute that here. Okay, so our potential energy is negative from kq, and then r negative 2, and then dr. So far, so good. And then we'll call this thing radius at point A, and then radius at point B. How's that? What that means is, you know, whatever this radius, right? If you draw the radius here, this radius to that radius. Get it? Okay. Then after this, it's just a calculus. Okay. We have k, q, and then r to the negative 1. Therefore, we make this positive. Good? Say yes. And then we evaluate this from r at point A to r at point B. Good? Okay. Now, and this minus that, so we have kq, and then 1 over r at point B minus 1 over r at point A. That makes sense to you? Good? Okay. So it only depends on the radius, radial direction, even if it moves sideways, because of this dot product, cosine theta. Okay. Now, the way it's written right here, do you see that our point at radius at point A is smaller than radius at point B, right? Do you see that this whole thing is a negative quantity then? For example, if this is 1/3, this is 1/4, let's say, and this is smaller, so 1/3, and that's a negative quantity. Whoops, what happened? Is it okay or is it good? We get negative potential. And then when we multiply this by the Q naught, then we get negative potential energy. Is that okay or not?
I think that because the field here is directed away from the point instead of toward the point, it actually is an increase.
Right. This is a lower potential right here, and this is higher potential, isn't it? So of course, if you go the other way, it's same as like bringing the stuff from up there to down to the ground, and that's got to be negative. You know what I'm saying? So we're okay. In realistically, we should have moved this thing from point B to point A. Then we'll have a positive potential energy. That makes sense to you? And then even this, we'll call this delta V, because potential energy is a relative energy anyway. Good? Okay. So delta V, people call this potential difference, and you will hear this word a lot later in circuits, potential energy, potential difference, okay? And potential energy is you multiply whatever the charge that you need to move, and that gives you potential energy. So I'm going to write it here. Delta U is equal to your Q naught times delta V, okay? Alrighty. Okay, I think I talked about potential versus potential energy already, so I'm gonna just delete this out. Okay. Now, or the other way of thinking about it is what happens if this charge is negative? Then it makes sense, right? Because you want this to be higher potential because everything is attracting, so you go that way. You know what I'm saying? Okay. So it depends on whether the charge is positive, negative, but or you can just put negative Q here. This as a negative value, then it reverses the direction anyway. Good? Actually, no, I take this back because I want to have this potential general definition. So potential is relative term, right? Something minus something. But it's more convenient to define zero potential at some point, correct? Usually in potential energy due to gravity, is ground is a zero potential, and then from there you go. If you go below, then it's negative potential. That kind of idea. So how do you want to define this thing? What is a zero potential, and what makes sense to you? One of this thing, if it's infinity, it makes perfect sense, right? So we'll choose this to be infinity, our starting point. Okay, so the correct concept, it makes a little more sense to, how do I want to say it? Because usually in order to have a higher potential, you want to start from far away and then move towards it has higher potential, right? You are doing the work. So you will move this charge from infinitely far away to your, because you cannot get there because that force between the two, this is reaching singularity and it will be infinitely high, right? So what we want to do is define just potential, and the potential is defined this way. Potential V is negative from, instead of A to this thingy, we'll just say R at some point B, and you put infinity here, of E dot ds. Okay, and that is the same as, let's just use our calculus term, right? This A approaching infinity of, and we can recycle our work as exactly same integral, kq r over, and we'll put r at point B minus 1 over, this is A, and this thingy approaches 0. So you get kq over r at point B. That makes sense to you? Right? So this is the potential due to any charge, positive and negative. Because negative meaning we just put negative quantity here, so it's negative potential energy. And I have a diagram that illustrates this beautifully. So if you think of it as some kind of a mountain, because you've seen this graph before, right? Higher potential, so if you release a ball due to gravity, it wants to move far away towards infinity. So potential energy is from the infinitely far away, you move it up. And this is an illustration of positive charge here. And this is negative charge here. Because negative charges attract, so if you release something here, then it'll start from this point, and then it'll fall in. That makes sense to you? Or if you release it from here, positive charge, then it'll just go. Right? So for that reason, not just, I mean, it's easier to understand with the electric charge, positive and negative, but gravitational potential or potential energy, would that be positive or negative then, from this context? Anything that is attracting has to be defined with negative potential energy. Because infinity is 0, and then it's attracting. You know what I'm saying? So from the surface, if you want to elevate it, you have to have higher and higher potential, which means infinity is far away, but you don't want to have anything infinity, so we define that as 0, and then coming back towards the Earth is a negative. And then it's only the net difference, the potential difference that matters, right? So if you subtract two negative numbers, you can still get positive number. That makes sense to you? So for that reason, you might hear this later in mechanics as well. Gravitational potential or potential energy in out there, not just MGH on the surface, but out there, is defined as negative energy. And potential energy only makes sense as in a relative term. So as long as if you go out, then you get positive difference, that's all that matters. So this illustrates everything. So to recap, potential is just this. And then if you want to calculate potential energy, then that is your Q naught, whatever the charge you bring into this field somewhere, Q naught, you know what I'm saying? Positive, times your potential, you get it? And it becomes K Q naught Q over R. Good? Okay. The other beautiful thing is, remember when you have like different charges in this configuration and we have to calculate the electric field here, then you have to do a vector sum of these, right? This is scalar. What? How did that become scalar? Wait, whoa. We had a vector before. Electric field is a vector. Force is a vector. How do we have a scalar after the integral? What just happened? Yeah.
Is it something to do with the infinite distance?
No. It's right here. Dot product. If you dot two vectors, that gives you a scalar. And that's how this thing is. Because you don't want your energy to be a vector. That energy has nothing to, especially potential energy, hopefully that has nothing to do with the direction, right? Higher elevation has a higher potential energy. Or in case of electrostatic force, far away, right? So this is a scalar, which makes our calculations so much easier because we just add scalars. So I have an example, this example. Okay, we are just calculating the potential, electric potential, point P, and P is right there due to these two charges, okay? Okay, so we'll calculate potential due to, we'll call this thing Q1 and this thing Q2 for the sake of our sanity. So potential due to Q1, okay? That has to be K Q1 over R1. You know what I'm saying? So what we have is K times 2 microcoulomb. I hate numbers. Can I just leave it? Can I just write it like that and have you guys substitute it? And this is 4 meters. You know what I'm saying? Okay. And then V2. That, of course, is K Q2 over R2. Now you have to be careful. R2, of course, is this, isn't it? Do you see it's 5 meters? So this is K Q2. Q2 being negative, actually here I'm going to write it, negative 6.00 microcoulomb over R2 being 5. Good? Now the total potential, of course, is just V1 plus V2. How about that? Good? This is part A. Well, what about part B? What is the potential energy due to this, right? Potential energy, of course, total, is by putting Q3, right? So Q3 times the total potential, and it's that easy. So potential is, you remember in physics, instead of doing kinematics and then acceleration, distance, which are vectors, when you started using energy, it was much, much nicer, especially the potential energy, MGH. So it's kind of like that. Energy is so much nicer So potential is so much nicer than field. You get it? Because you have to integrate the field with a dot product to get the potential. And then you just substitute whatever. Okay, how about that? Alrighty then, moving on. How do you figure out the field from the potential then? Let's recap. Our potential was negative here, E dot ds. It's an integral. It's some kind of antiderivative. So that would tell you that E has to be some kind of derivative. You know what I'm saying? Of V. What kind of derivative are we talking about here? See, there are two kinds of derivatives, right? Derivative with respect to time and derivative with respect to space, right? X, should we put X here? Something about that doesn't look right. Why not? Because X is just one direction and we'll happen to be living in three-dimensional space, or the problem usually is at least two-dimensional problem, so that ain't right, right? So what come, this is a derivative with respect to space, but what are we talking about? Del. And remember there's a vector harpoon there? So this will take the derivative and convert it back to vector. And this is what del is. Just gonna tell you what it does. Partial derivative with respect to x, I vector plus partial derivative or whatever that thing is with respect to y, j vector, and then don't weird upside down. Just think of it as d dx for those of you who are not familiar with multivariable calculus. You're holding, when you do this, you're holding y as a constant and just taking the derivative, the usual power rule and stuff. Okay? And then plus partial derivative of this with respect to z, if there is z. Usually in our case, there isn't any, so it's two-dimensional, and with respect to k. Okay, so this thingy is known as a gradient. This is known as gradient vector. You take a potential function and you take this derivative. And then people just write this thingy like this. I first, so that you can put some function here, right? Plus j plus k. That is a great, they'll operate. You know that this is an operator, right? So this is a 3D version of that. Or 2D version, then you just take these two. I know, I just scared a whole lot of you. For our purpose, it's a lot easier than this. This is like general multivariable calculus in 3D all blown out, chapter 17, which they haven't even learned yet. But in reality, things reduce down to one-dimensional problem. Okay, so we'll just take this. Okay, we have electric dipole. Okay, Q, positive Q and negative Q, same distance. Okay, now we have to calculate the electric potential from point P, there, and then point R. You know what I'm saying? So 2 point P is here and R is here. Because remember, when we are calculating electric field, we have to do a vector addition, which was complicated, right? So we'll take a derivative and get exactly the same expression, okay? So, which one? I guess we'll do A first, okay? So here's A. So potential due to positive Q, okay? This is KQ over A now, right? Your distance. Okay. And then your potential due to negative Q. Oh, I screwed up. Distance is not A. It's this distance, right? I just write R. And that is K, Q. What is the distance, location of P? Do they tell you? On the y-axis, any P. We'll just call this thing Y. How's that? So it becomes a function of Y. You get it? Okay, so this is K, Q over square root of y squared plus a squared. Good. Okay. So then potential due to negative Q, that'll be K negative Q over R. Good. So you have negative KQ over square root of y squared plus a squared. Say yes. Okay. Now, potential total is this. Wow, it's 0. Wait, does that sound right? Zero potential? Does that sound right? Yes, no, maybe.
Sort of looks like, seems like there is usually a flow between the poles.
Mm-hmm. This is the situation. We are right there, right? Does it make sense to you? That's 0 right there? Because it's positive here, and V is negative here. So it's 0 in between. Oh yeah, it is right. You know what I'm saying? Because everything flows from positive to negative, so that direction is still there. There will be an electric field. Zero potential does not mean zero electric field. Good? Okay. We'll do the second one. Okay. Now calculate the potential at point R, x units away from it now. So potential due to positive Q is still KQ over our distance R, which happens to be KQ over x plus A, oh, square root of x plus A. No, it's just x plus A, right? A is just physical distance, so this distance plus that distance, good? And then potential due to negative Q is equal to K negative Q over the distance, right? Which is negative K Q over this one is x minus A, okay? Because that's this distance right there. Okay, now we have to add, and these things don't add as well. You know what I'm saying? So the total potential is the two potentials added together. And we'll just, there's no other better way, so we'll just write it like this. Minus KQ over x minus A. Okay? Or if you want, I don't know why, you want it because you want to differentiate it soon, so we'll just write it like this. KQ, and then we have x plus A, negative 1 power, minus x minus A, negative 1 power, like that. Good. Okay, then, now we want to find the electric field in x direction. Actually, in other direction, it'll be 0, but they really don't want to make you do gradient and all that crazy stuff. So they just do a electric field in x direction. And that happens to be partial derivative with respect to x of your total potential. You get it? You know what I'm saying? And that, because remember my gradient here is with respect to x, y, z as well, but they just want this one. Get it? X component of this whole thing. Okay, so differentiating that thingy, eh? With respect to x. Well, that's easy now. So we have kq here, and then negative and x plus a to the negative 2 power plus, this becomes, yeah, plus x minus a negative 2 power. How about that? Let's just convert it back and see if it agrees with our previous idea. So this is then negative kq over x plus a squared. And then the other one is kq over x minus a squared, like that, eh? Okay, let's look at the diagram. Oh, something does not look right. Because we're getting the opposite answer. Yeah, huh? I screwed up here, right? We need a minus sign there, right? Because the way we defined it, we have a minus sign here, right? So we want to put opposite of everything. Okay. So our answer, we want to change our answer. This sign, we just need the opposite sign here, right? We just need minus sign there, and then minus sign here. So that makes this plus and this minus, and that's exactly what we want. Because if you think about it, this is from last time, right? This is KQ over R1, if you will, right? And this is negative KQ, negative sign over R2 squared.